Usnees, but yeah.
Hello. Yeah.
Hi.
So, yeah. Good morning, everyone. Thank you for the invite. I'm Siddharth. I work at IIT Bombay. And so let me just, So is the cursor visible to you? Is the mouse visible to you?
Yes, it's visible, yes.
Okay, great. Yeah, so I belong to the Department of Physics here and also the center called the Quantum Information Computation Science and Technology Center of Excellence, long name, but we call it QIQT. And thank you for the invite. So from what I understand, this talk is 45 minutes and it's supposed to cater to a diverse range of people in the audience and also primarily to introduce a lot of undergraduates to what's going on in terms of research in the different verticals of quantum technologies. So that's why this talk is really at a colloquium level. And what I've tried to do is basically three main sections, each of them pretty small. And in the first section itself, I've tried to really quickly summarize what we want to do with a quantum internet or a quantum network and what are the problems there. In the second half, I have wanted to go second thirds. I have wanted to take a step back and look at how far we have come in our understanding and appreciation of entanglement as a resource. And in the third part, I have tried to highlight some of the current and potential uses of entanglement. So with that, let me start by pointing out that efforts at making the quantum internet are taking place worldwide, including in our country, which is, as you must be aware, recently launched the National Mission on Quantum Technologies. And one important vertical of that, of course, is quantum communication. So, of course, a quantum internet will allow us to do quantum communication, and we'll see what that gives us for the huge amount of effort that it will take. So, okay, so quantum internet, if you think of it as a device or a system, these are its features. So essentially, think of everything you can do with the classical internet. You can do classical communication, you can do remote tasks, you can do distributed tasks, and then throw in some resource, some quantum resource, which is entanglement. So if you imagine that the green dots here are the nodes of your network, so these green dots have spatially separated quantum systems. So they are the nodes of some network. And between those quantum systems, there is entanglement. So what this resource would allow us to do are things like secure communication between the nodes. You could have a global network of clocks which share entanglement and keep time very precisely using such a distributed network of clocks. You could do distributed quantum computation. So you have some quantum server and the local machines can communicate using quantum communication with the central server. So you could perform distributed quantum computation. And of course, you can use this resource of entanglement in a distributed manner to even perform fundamental tasks, such as testing Bell's inequalities with higher and higher precisions, closing all the loopholes to the best of your ability. So these are the features. Now, I apologize for the change of the scheme, but if I try to put in a little more technical material, and I promise this is perhaps the most complicated slide of the talk, to the cartoon of the quantum network, then what a quantum network does is basically it allows us, as I said, to classically communicate between the nodes of the network. It allows us, in the ideal case, to send noiseless qubits between arbitrary nodes and it allows us to distribute entanglement. So the kind of metrics or benchmarks that you would evaluate a network against are, what the channels of that network, what's the rate at which you can communicate bits, or what's the rate at which you can establish, you can send qubits, or what's the rate at which you can establish e-bits between two distant nodes. And so the end goal, as I said, is to be able to send a qubit noiselessly between arbitrary nodes. So A here is, say, the initial node where I have quantum information in terms of this superposition alpha 0 plus beta 1 plus gamma 2. And I have kept the dimensionality of the system as 3 because I would like to point out that we don't necessarily restrict ourselves to qubit networks. You could have arbitrary dimensional quantum systems at the nodes interacting with other such systems at other nodes. So this is some quantum information at node A that you would want to send over to node F. And so the restriction to the kind of quantum operations that you can do on this network in order to achieve your end is that you can only do LOCC operations. So local operations, you are allowed to do coherent measurements or coherent unitaries on all the quantum systems at one node. And you can coordinate your actions at one node with some other agent at some other node using classical communication. But what you're not allowed to do is, for example, a coherent operation on one qubit A in Kolkata and another qubit B in Bombay. So global coherent operations are not allowed, local are allowed, and you are allowed to coordinate your actions. So very roughly, the nodes and the channels of this network, you can divide them into stationary qubits and flying qubits. So stationary qubits are the systems at the nodes, and typically they are the ones to receive quantum information through the channels and process them. So you could have these nodes comprising of superconducting qubits or trapped ion qubits or atomic ensembles if you're interested in quantum memories. And these stationary qubits interact with other stationary qubits at other nodes via what are called flying qubits. So these are carriers of quantum information which transmit quantum information from one node to the other. And even there you have multiple choices. You can have discrete flying qubits where, for example, if it's a single qubit, then you can use the polarization modes of a photon in order to encode the zeros and ones. You could encode this in the time domain where the different arrival times denote zeros or ones. You could have continuous encoding where the quadratures of a beam of light are actually used to encode zeros and ones. So we have a lot of freedom in how we can design and implement a quantum network. So of course, between these nodes, you need to have actual physical channels, which can also be of the fiber optic type. So if you are thinking in terms of a metropolitan area quantum network, that seems to be the most well suited for that kind of a small area network. You could have free space communication via satellites, for example, which connect networks over much larger distances. And when you consider quantum networks at very, very small scales, separated by centimeters or millimeters, you could also have cavity modes acting as the channel between two qubits. So for example, here the two pink circled cavities actually are qubits which communicate via this purple colored, via the modes of the purple colored cavity, which act as the communication qubit. And of course, experimentalists would know this much better, that a lot of the bottlenecks surrounding the implementation of quantum networks is hidden, of course, in the details, like what kind of entanglement sources do you have? Are these photonic? Are these solid state? What kind of interfacing? So you need frequency conversion between the energy ranges at which the stationary qubits process information and the flying qubits transmit information. And you need high efficiency detectors, otherwise your rates are very, very low, right? So that's how, but this is the broad outline of the efforts that it would take to implement a quantum network. Okay, so as I said, when I flashed the first slide, that you could do secure communication. And so very roughly, the idea is that if two nodes of the network, A and B, want to communicate securely, then what they can do is that they can use distributed or shared entangled states to perform independent measurements at the two nodes. And then via certain information theoretic procedures, which are statistically proven to be safe and secure, you can create a list of random bits, common random bits, which is called the key, that you can use to encrypt your message by a simple Zoring. And then because both parties share this key, a further Zoring at the receiver's end can decrypt it and yield the message. So essentially, quantum cryptography is the idea of classical secure communication based on establishment of a common shared key, based on measurements, independent measurements on a distributed and shared common entangled state. So that's very roughly what quantum cryptography tries to achieve. Entanglement-based QKD has been, in principle, demonstrated over a long distance, such as over 1,100 kilometers, by actually placing an entanglement source on a satellite, which then creates a pair of polarization entangled photons, which are then beamed to Earth stations. Independent measurements are done. Entanglement parameters are established based on which you can extract what is called a finite secure key rate. And I encircle that to highlight just at this point of time, just how small it is. So it's about 1/10 of a bit per second. Compare that to classical communication rates over the internet across the globe, which is, if you wish it to be, definitely in the range of gigabits per second, right? So quantum communication over long distances based on entanglement, quantum secure communication over long distances based on entanglement is possible, but at this point we are rate limited. And I'll come back to this point later. So what else can entanglement give us? It can give us, so remember when we did secure communication, we were still sending, our end goal was still to send classical communication, but in a secure manner. But we could actually require quantum information to be sent from point A to point B. So quantum information, if you leave apart the nuances right now, for me, is just a state, psi c, and it's in a superposition state, alpha 0 plus beta 1. And the point is that I don't know what the state is. So unknown and arbitrary states could come to A, and the task is to send it over to B. And so it's not that, for the uninitiated, if this task sounds pretty simple, remember that you are not measuring multiple copies of this state to figure out what alpha and beta are, because that would correspond to just sending over classical information. Once you determine what alpha and beta are, that would correspond to sending classical information. So you have unknown and arbitrary quantum states coming to you, and the task is to send it over to B. And this is possible using the primitive called teleportation, quantum teleportation, where essentially the agent at A will perform joint measurements on a joint operation on C, the system C, which has this unknown state, and another qubit in possession of A. and then perform some measurements and send over the information, the classical information of the measurement outcomes to B, who then acts conditionally. So based on the information arriving from A, agent at B would act conditionally, apply some unitaries to actually retrieve the state C back at B. And remember, in teleportation, what happens is that the state is transferred, but no copy of it is retained, or no information about that state is at all retained. So teleportation is a way to send unknown and arbitrary quantum states over to the receiver without the sender knowing what that information is. So this would be what is really transfer of quantum information as compared to the QKD or the quantum cryptography task, where we were really trying to secure classical information. So as an example of what teleportation can help us do in a quantum network, for example, is something like this. Let's say, it allows us to do what is called entanglement-enabled interferometry. And the point is that you have this diffused source of weak light, and you would want to resolve points on it. So that's you would want a high resolution. So you should be able to resolve 2 points, even though they might be very close to each other on this diffuse source, right? And one way to do that is to have what is your optical aperture large. So optical aperture is typically synthesized by placing small receivers, but far apart from each other, which then bring the collected signals together for interferometric analysis. So what happens in this case is that when you try to collect the rare single photons, because it's a weak source of light, together for interferometry, then often you lose these rare signal photons in the transport channels. So that basically degrades your signal to noise ratio. Whereas if you compare that to an entanglement-enabled setup, where basically these telescopes would share entanglement and then perform local operations such that the quantum information is transferred, right? But you don't really need to actually physically transport the single photon, then you can maintain a high signal to noise ratio even when these telescopes are far apart, as long as you can guarantee that you would provide the entanglement resources for teleportation to happen efficiently, right? So the whole task of maintaining or even improving the signal to noise ratio is transferred to the task of actually distributing high quality entanglement at sufficient rates. So in fact, one estimate for an improvement of this kind of resolution is that for a certain existing optical interferometry setup, you could improve from milli-arc seconds of resolution to micro-arc seconds of resolution using about 20 qubits per site and 200 kilohertz entanglement generation rate with a 30-kilometer baseline. So 30 kilometer separation between the telescopes, 20 or so qubits per site, and a certain amount of entanglement generation rate, which even now is not that realistic, as you will see. So I flashed my first slide and I talked about a few different, I just mentioned a few different applications of a quantum network. Then I talked about two specific applications, one in which cryptography, in which the goal is secure classical communication, and then interferometry teleportation, and then based on teleportation, interferometry, where the task is to actually send over quantum information, right? And in both these cases, we saw how entanglement might be useful. So that's why entanglement, I call entanglement a feature of the quantum internet. So quantum internet is classical internet plus entanglement as a feature. But then, as with any system, you would have bugs. You would have bugs in the scheme that you want to devise, in the in the phone that you have, in the software that you write, there would be features, there would be bugs, and so the bugs here are the fact that these channels that I talked about, right? When you want to design and build a quantum internet or quantum network, they are lossy. So you lose. So for example, that entangled photon source on the satellite, which creates this connection over 1100 kilometers, right? That has to suffer loss because these photons are lost in the atmosphere. There are challenges in how you can actually point to the receiver. So beam tracking is a big problem. Then there is atmospheric turbulence. So you lose a lot of the signal that way. In fact, for most schemes, and definitely fiber-based ones, you have an exponential loss with the total length over which you want to distribute the entangled state. Then there is decoherence. So loss is that you lose the quantum signal completely. But even when you do receive the quantum state or half of the quantum state, right, the two halves go to the two distant receivers, you may have actually sent a signal which is in a perfectly entangled state, like a 2-qubit maximally entangled state, such as a Bell state. But because of decoherence, you will lose the entanglement quality of that state. So ultimately, a 5+5+ state, so 5+ ket, 5+ bra, so projector on 5+, would decohere to something like, some probability of 5+ plus, so some plus some maximally mixed state, so the identity on 2 qubits, so some noisy version of 5+, right? So something like the Werner states or the isotropic state. So which don't have as good or as much of an entanglement as the initial state that you set. So these are the two bugs that you would face. And of course, what you can do with the quantum internet or a quantum network is limited by the fundamental constraint of no cloning, the no cloning theorem. So no cloning theorem in quantum information is this idea that you can't have a device, based on the known rules of quantum mechanics, which allow us to do this, which basically takes one copy of an unknown state, right? And it takes another blank state, like a 0 state, so some state initialized to something that we already know, right? And gives me as output 2 copies of the unknown state. So this would be like a qubit copying machine, because if this were allowed, so the fact that this is not allowed is called the no cloning theorem. And I highly recommend you to read this Nature paper, which is literally double this. So basically there is just one more paragraph to this paper, and that's it. And it makes the simple point that because of linearity, you can't have such a qubit cloning machine. And so this is a fact of nature that we have to live with. The implication of which for the quantum internet is this, that, for example, when I want to distribute entanglement between A and F, as I said, because of losses, I might receive, let's say, 100th or a millionth of the number of entangled states that I actually distribute from C, half towards A and half towards F, right? So if I were able to copy and clone these, make multiple copies of these halves, then what I could end up doing is basically amplifying the quantum signal every time it is attenuated. So entanglement, I have a lot of loss in my network. So what I do is use these quantum amplifiers or quantum copiers in order to pump up my signal. But that's not allowed. That's not allowed because of the no cloning theorem, right? So we need a workaround around this problem. in order to distribute high rate and high quality entanglement between the nodes of a quantum network. That's the point, that's the constraint we have to live with, right? So the no-cloning theorem, as I said, leads to the fact that if I want the rate, so I fix my two nodes of the network A and B, right? And the distance between them is L. And I want to generate high quality entanglement. So the quality of that entanglement, you can parameterize by something called the fidelity. And so the higher the fidelity, the better the quality of the entangled state. So F equal to 1 is like a maximally entangled Bell state. And so what happens is that these, any scheme that you might devise, I would remind you the kind of schemes you can devise. So these all have to be LOCC schemes, and we'll talk about a particular scheme in a bit. Any scheme that you devise actually leads to the fact that the rate at which you can obtain these states falls very steeply, especially once you get closer and closer to the perfect Bell state limit, right? So the rate at a fixed distance falls sharply. And if you look at how this rate scales for the same fidelity, right, for the same quality of entanglement at longer and longer distances between the two nodes, what you find is that basically the rate falls exponentially. So the Y scale is the dB scale, right? So this goes linearly, which means that the loss actually is exponential. And so when you want to distribute entanglement, here, the rate is measured in terms of a derived quantity called the QKD rate. But the point is that you see this whole gray region where you don't use what are the indirect analogs of quantum amplifiers or classical amplifiers. So what are called quantum repeaters. So this gray area is without using such repeaters, you would find that the rate decreases exponentially. And so this red arrow points to the fact that in order to distribute entanglement in such networks, we have to work around the no-cloning theorem via theoretical schemes called quantum repeater schemes. So people who are interested in this kind of work, this is something that you would very likely get your hands dirty with when you start off, which is essentially looking at the design and analysis of entanglement distribution rates or key distribution rates for different kinds of quantum repeater schemes. So, and I'll talk about it briefly. And so the goal here is that, the DRDL is essentially, and the mod of that essentially is the rate at which the rate of entanglement distribution would decrease with length, or would decrease with separation between the two nodes. If we can minimize that, so essentially reduce the slope of these rate versus distance curves, that would mean that for very long distances too, my loss is still within acceptable and within the bounds that would allow me to perform some kind of end application. So essentially, the more quantum repeaters and the better designed quantum repeater nodes that you have in between your end nodes, you should be able to reduce the rate at which your entanglement or key rates decrease, right? So that is the problem. And the kind of theoretical expertise one can take advantage of in order to make this happen are basically ideas from entanglement theory and graph theory. If you imagine networks are graph instances of certain kinds of graphs with their own topology, with a definite weight structure. So the weight structure comes from the way you describe the entanglement generation process. So it's a multi-parameter vector which describes each edge of this graph. And so how you distribute entanglement becomes a question of what is called the Pareto optimization. Pareto optimization question in network routing. So these are kind of tools you would require in order to deal with optimization of entanglement distribution rates in quantum networks. Okay, so as I said, quantum repeaters are important. And so here, I'll very briefly talk about what quantum repeaters are, right? And so repeaters are a divide and conquer scheme where basically, instead of distributing entanglement from a central source like C, half of the entangled pair being sent to A, the other half being sent to F, what you do is you divide the distance into multiple small segments. You have independent entanglement generation over each small segment, and then you have independent entanglement connections at each intermediate node. And you can have entanglement purification, so improvement of the quality of distributed entanglement over short or long distances. So essentially 3 main steps to what are called the generation 1 quantum repeaters. So entanglement generation, entanglement purification to obtain higher quality entangled states, and then entanglement swapping, which is basically connecting two short range entangled states to obtain a longer range entangled states. And so I would just like to point out that entanglement generation is ubiquitous. You can do it pretty easily these days with SPDC sources, and a lot of the people who were awarded the Nobel last year had an important role to play, or at least one of them had a very important role to play in development of such sources, which can give us reliable entangled states as output, or entangled states as output reliably, right? And so this is experimentally feasible. Entanglement purification has also been demonstrated experimentally, and so has entanglement swapping been demonstrated experimentally. But all 3 steps of a quantum repeater for the same platform has not been so far demonstrated, in a non-laboratory setup. So that's what the state of art is in terms of experiments. But theoretically, we are, of course, far ahead of what are called the generation 1 repeaters that I just described. If you throw in little or some more bit of quantum error correction, you can reach what are called generation 2 and generation 3 quantum repeaters, which would not require, for example, generation 3 wouldn't require swapping in the direct sense. Generation 2 would require swapping, but it would swap in the encoded basis. So it is possible to alleviate some of the problems with generation 1 quantum repeaters, the primary one being that even when many of the experimental ingredients click, it would still be limited in the rate, the maximum rate at which you can distribute entanglement. So you can overcome that. You can have faster and faster entanglement generation rates, but this would require a larger number of qubits per repeater node. So for example, here, in principle, you can have entanglement generation over long distances, even with a single quantum system at each node. But for example, for generation 3, you need encoding blocks which are a few tens to hundreds of qubits in order for you to encode quantum information in a quantum error correcting block, which protects against loss errors and just one-way transmits the quantum information without the need for swapping and so on. So this is a very active area of research. How do you reduce the size of the encoding blocks? How do you reduce the required fidelity of the quantum gates, which would actually create such encoding blocks? If those things happen, and also experimentally, Dirk England's group at MIT and others are developing these photonic chips, which should be able to perform some of these operations to create these large photonic encoding blocks. So that's what I would like to talk about quantum computer generations. And now I would like to just take 5 minutes to draw your attention to the fact that, in the last few slides, what we saw was that entanglement is a resource. We don't even these days, or at least people who work in the applied quantum information areas, we hardly take a moment to even doubt the fact that is entanglement real or not, right? Or is entanglement, does it make physical sense or not? However, this was not always the case, right? So, the fact that it has taken us pretty much the entire grief cycle, or the equivalent of the grief cycle, in terms of accepting and now appreciating and actually being enthusiastic about entanglement. It has taken us essentially all the stages of all the analogous stages of grief. So, there was denial. If you consider the Bohr-Einstein debates, right, as to what is the meaning of a quantum state such as the EPR pair, because it does not seem to obey the postulate of local realism, right? And so there was anger, anger in the sense that a scientific criticism about the validity of quantum theory as overall, right? Then there was bargaining, in the sense that what features of the new quantum theory at that point we could keep and we could do away with. And then there was, excuse me, suggestions, constructive suggestions for testing out what nature really might be, whether we need to accept local realism as a fundamental postulate of nature or not, or let nature tell us via experimentation whether locality is something that she obeys, right? And so from these theoretical prescription for an experiment, we had another form of that proposed form of that experiment, much more amenable to implementation. And so that experimentation, upon multiple rounds of refinement, actually has led to a situation where we have not only tested the fundamental validity of entanglement as a physical phenomena, but we have also, people have pioneered quantum information science and technology, right? So because of the fact that, so I think it's noteworthy that, so in order to close what are called the loopholes of these bell test experiments, people had to design better and better scientific equipment. And a lot of that actually has a very important role to play in the current hardware of quantum technologies, and definitely so in quantum communication. So I will just point out that the EPR Gedanken experiment basically postulated that local realism should be a part of nature, whereas the subsequent experiments actually invalidated that idea that you can have quantum states, certain quantum states with correlations that do not obey locality, that violate local realism. So nature in its most general sense can be non-local. And so from that background, I jumped to this slide where actually right now we have, I would say, a very, of course, compared to that, a much better sense of what does entanglement mean, because we know what does it mean operationally. So what does operational mean? It means that if you tell me that, you give me 1 kilogram of ghee, for example, right? I know that I can fry maybe 100 puris with it, right? So 1 kg as a weight doesn't mean much if what I'm interested in is operating with that ghee, right? What does it give me in terms of the task that I want to achieve? So operational means what is it that I want to achieve, and can I assign to a given amount of resource a value that tells me to what quantum am I able to achieve the task that I desire. So for example, right now we understand what different entanglement measures mean in the operational sense. So for example, you give me multiple copies of some, let's say some pure state which is entangled but not maximally entangled like the Bell states. If you give me a certain number of copies, I can do what are called the LOCC class of operations and purify the entanglement such that given some number of copies n, I'm able to extract m Bell pairs or m perfectly entangled 2-qubit states. So in that case, I would call the ratio m over n as the fractional yield of Bell pairs, and you could connect that with a theoretical estimate of the entanglement, which is the entanglement entropy of the state. So right now, we know what a given amount of entanglement entropy for a state means in terms of its operational significance. That is essentially the ratio at which I can extract a certain number of Bell pairs when I'm given a large number of such initial states, right? So we know how to purify entanglement and how to estimate the number of purified pairs that we can get. That's one operational meaning. So what does it mean for the end task of teleportation? So if I'm given a maximally entangled 2-qubit state, so a Bell state, which would have an entanglement entropy of 1, it essentially means that I would be able to teleport an arbitrary unknown quantum state with perfect fidelity. So with no error, would I be able to teleport the quantum state from A to B. So that's the operational meaning in terms of teleportation when I'm given 1 unit of entanglement resource, right? So there are funkier stuff that I can do with entanglement. So something called catalysis. So there are, if I'm given some state A and B, some state psi on 2 parties A and B, and I'm interested in affecting a transformation of the state from psi ket to psi tilde ket, but I would not be able to do that given the restriction of LOCC operations. It turns out that throwing in another auxiliary pair of systems A prime and B prime, which are in a state C, which has some amount of entanglement, but a very particular amount and a particular form of entanglement, I would be able to implement this transformation and get that extra state back. So something that is reminiscent of a catalysis, of a catalytic chemical reaction. So my point is that we now operate very freely with entanglement as a resource, starting from initial skepticism and a lot of vigorous debates about whether entanglement is real at all or not, right? So, okay, maybe I wouldn't have time to flash to wait till you till you finish reading this, or maybe you already have. So my point is that with this renewed understanding, we apply entanglement at a lot of places now, right? So I talked about cryptography. I talked very briefly about this experiment, but you see, our understanding of entanglement has actually also led to better ways of classically uh, uh, countering the problems that entangled quantum states might have for simulating certain quantum computations. So for simulating certain entangled computation. So basically, if we understand the structure of entanglement, whether it is local, whether it is long range, in the quantum states that we are interested in the quantum states of some system that we are interested in, then we would be able to basically create ansatses for treating the evolution of that system such that these ansatses are computationally efficient to deal with. So that is why you have these matrix product states or multi-scale entanglement renormalization ansatses, which help us simulate certain entangled quantum computations classically. Not only is so, there are two cases that I talked about for cryptography and for teleportation. They were, in a sense, more quantum communication uses, but people have shown that quantum teleportation is actually what is called a universal quantum primitive. So just like you teleport quantum states, you can teleport quantum gates and actually create controlled unitaries on systems A and B, which are not directly interacting. So this idea, for example, can be extended to form what are called distributed quantum processors. So a small scale quantum network of distributed quantum processors can, in principle, remove the bottlenecks with scaling the sizes of quantum hardware. So one problem that people are facing in ramping up the size of quantum hardware platforms, right, is that there is a whole different scale of problems that emerges when you go from, let's say, 20 qubits to 100 qubits. And another scale emerges when you go from 100 qubits to 1,000 qubits, much unlike what you could do with semiconductor chips, where you can just keep packing in more transistors without really facing any problems till you exhaust Moore's law, right? So right now, people are facing this problem where already billions of transistors have been packed together, right, or packed close together. So that is not the case with qubits. For many platforms, the problem is that 20 qubits, 20 is a ballpark number. I'm saying, some tens of qubits you can pack, you can connect well, you can control well, but the moment you go one order of magnitude higher in terms of the number of qubits, those same designs don't work. The controls become very bad. The qubit fidelities, the gate fidelities become very bad. So scaling is a problem. So instead of that, you could have a small network a network with many small processors. Anyway, so I won't have time to go through this. The point is that those were some of the applied uses. We also have some fundamental uses of entanglement, such as understanding entanglement in random quantum states. How does entanglement evolve and what does it tell us about equilibration? So how does, for example, an isolated quantum system thermalize? These days, people are trying to understand information scrambling. How does information delocalize in a quantum many-body system? And of course, as you can imagine, entanglement between distant parties is a key tool in understanding that. Importantly, a quantum network, states on certain quantum networks have been used to demonstrate something very fundamental, which is that if you have quantum theory based only on real numbers, then it can be experimentally falsified. So complex numbers, in fact, are a central ingredient of quantum theory and not something incidental. Okay, so some questions with quantum networks are that instead of just bipartite entanglement, what can you do with multipartite entanglement measures? How do you do entanglement swapping? Looking at entanglement structures, so entanglement cliques and entanglement domains. My current work is actually regarding what are called the quantum safe regions of a network and a quantum resistant region. So quantum resistant regions won't have high enough average entanglement between any two nodes. And so you would be limited to what are called PQC, post-quantum cryptography protocols in those regions. Whereas quantum safe regions highlighted here in blue would have high entanglement and high rate regions converging. So these circles are in terms of increasing graph distance. And so in these regions, you could have QKD protocols, efficient QKD protocols, and they would thus be quantum safe. Finally, congratulations, we have together arrived in the quantum domain. And here is a QR code to check out our center website here. So with that, let me stop and thank you for your time.
Thank you, Sandra, for a very nice talk, nice colloquium. And we are open for the discussion and questions and comments. Is there any comment, question? Yeah, Sangeet. Sangeet, go ahead.
Am I audible?
Yeah.
Yeah.
So yeah, I just want to ask something about these catalysis operations. Like, so you mentioned that in those kind of operations we use another state to catalyze these kind of reactions, right? Like,
yes.
So can these states be entangled or?
They have to be entangled. You cannot catalyze. Yeah. So like this psi, right? Of course, psi and psi tilde both are entangled, right? And in fact, there are results which show that if the entanglement value of or the entanglement measure of psi prime is less than that of psi, you can perform this operation using LOCC, right? Using LOCC. Now, that is why you would desire this entanglement transformation to be in the direction of upward. You would desire the entanglement transformation from psi to psi tilde such that this has a higher amount of entanglement, right? What this catalytic state or what this ancillary state would allow you to do is to perform this operation, which is called entanglement assisted LOCC operation, such that you can get psi tilde probabilistically. So ultimately, remember there has to be a non-increase of this. So you cannot increase this non-local measure of entanglement using LOCC operations, right? So ultimately, you can achieve this bump in the entanglement measure probabilistically. Yeah, and to your question, yes, this catalyzing state needs to be entangled. It cannot be a product state.
So does this entanglement assisted LOCC still classify as a traditional LOCC operation? Like, since you said that it could give us a higher entangled state, but since it is probabilistically, the total entanglement would still be on average equal or less than the initial state, right?
Right. Yeah. So you can, people call it, I've seen people call it entanglement assisted LOCC. Yeah. So, strictly the LOCC paradigm is you are only allowed classical communication because here, the two parties also share entanglement. You don't restrict yourself purely to CC. So that's why people call it ELOCC.
Okay. Yeah.
Okay, Sumit. Yeah, thanks for your question. So there's one more, Ranjit.
Yes.
Please go ahead.
Yeah, thank you for your presentation. I have one question. In one of your slides, you have mentioned about losses. So, my question is, could you please name type of losses in channel like satellite and ground? For example, photon loss, diffraction, depolarization, maybe any other. So could you please?
Let me just, maybe this is the best. I'm making a distinction between losses and decoherence. So something like depolarization, I would classify as decoherence, right? And you're right. So in the loss mechanisms are different in different media. When you have fiber optic channels, you can have diffraction. And I'm not an expert in fiber media, but for example, I know that there are things like PDL, polarization dependent losses. So what happens in that case is that suppose I encode my entangled states in 0, 1 as horizontal and vertical, right? The different polarizations would suffer different amounts of losses. And so this, in addition to loss of the signal, actually gives rise to a decoherence because the different components are, there is a differential matrix of losses between the two components. So ultimately, in terms of applications, what we would do is that basically we would take a channel, calibrate it in a phenomenological manner that this is the amount of entanglement that I'm sending, and this is the amount of entanglement that I'm receiving. So typically they are measured by some fidelities. So fidelity in, fidelity out. And so the overall channel would be characterized that way. Yeah.
Thank you.
Any more question? No. Okay, maybe I have a question.
Sure.
So you mentioned about the quantum internet. So quantum internet, I mean, how this, I mean, if I understand correctly, then the classical internet, and there is a, what we get from the quantum internet, what extra we can get from the quantum internet than what we already have in classical internet.
Yeah. So, okay. So right now, short answer is that you will get at the very least unconditional security for all your communication.
Yeah.
So for example,
okay, let me now, when you said about the security, so how do you ensure this security? In which way?
Yeah, so the simplest would be QKD, right?
No, QKD is not a secure one. QKD, you have to prove a QKD is secure or not.
No. QKD is unconditionally secure.
QKD is just quantum key distribution. Whether it is secure or not, you need another protocol to test this, whether your quantum key distribution is secure or not. Okay, for example, as you say, QKD, yeah.
So let me point out this. So if you are doing QKD, right, and you your equipment measures a certain parameter, which you can experimentally do. Actually, in QKD, people measure what is called the QBER, quantum bit error rate, right? So if you can measure that, it will tell you, that parameter tells you for every round of QKD, whether you have security or not. And in terms of, so to your answer, there are two things. One is theoretically QKD is unconditionally secure. That is why people are trying to do QKD. Now, if your question is...
If such a QKD is based on Bell's theorem, right?
Yes, so...
Not the BB84 one.
No. So BB84, so that's the thing. So, if you can do BB84 over arbitrary distances, then it's secure, but you cannot do that. That's why you would bring in trusted nodes. And then what happens is the vulnerabilities of your system go into how secure your trusted nodes are. So one example is here, right? You want to do QKD between A and F, and you want to do BB84, but if you can send the BB84 signals directly, right? Which you cannot. Then, so if you could do BB84 directly between A and F, it would be secure. But you can't do that because the rates are very low. So you would
then let me tell you let me ask you one thing. What certifies BB84 protocol is secure? Even in arbitrary distance, what certifies it? For example, if you have an entanglement, in such a case, you have a Bell's theorem, a Bell inequality violation. But
in that case, the QBER, the quantum bit error rate.
Quantum bit error rate.
Yeah, QBER.
Okay, but okay, keep aside this question. But in a long range or in a network, so network you need a Bell inequality, right?
You don't necessarily need a Bell inequality. So, like, what is your goal?
Wait. Bit error rate is nothing. Something. Can you certify that bit error rate, whatever you're getting, this how it certifies? Because this is not a physical principle, right? So I mean, you have bit error rate, maybe it's related to your Bell inequality violation. Okay, so then in whole network you need to show some Bell inequality violation. Otherwise, I can always say that I can have a classical model, I can mimic your whole data, or maybe there's a presence of Eve that is collecting the data. You will never know.
Right. So you see what you're referring to. So remember in BB84, what you do is after you initially distribute the state, you do some XZ measurement, some measurement in independent basis, right? And then you would use a public and authenticated channel to do your basis reconciliation and privacy amplification. So these are steps which statistically tell you whether there has been some eavesdropping or not, right? So essentially, this QBER measurement is at this stage where you get a sense of how much eavesdropping there has been or not. So if the bit error rate is, I believe, above like 11% or so, then basically the whole key distribution round is discarded. So that's for key distribution. The other thing is that you're talking about certify non-locality or not. Yes. So in terms of in terms of in terms of the quality of the entangled state that you have distributed, yes, that's what you would do. You would do the analysis of the S parameters, for example.
No, I just wanted to see that maybe I'm running out of time. You said there's a repeater experiment A to A, you have a repeaters, right? So every point of node, every middle node, you are performing some Bell basis measurements and you are getting that one. So then every time you have to certify this. Otherwise, it is not secure, because in the two-party case, it is secured by the Bell's theorem. Whatever you are saying, that bit error rate, that's related has to be related to the Bell's theorem. Otherwise, it is not secure. So in that case, also repeater case, you have to, at every point you need a mechanism so that you can certify that I cannot mimic this by a classical model. Otherwise, I would have used the classical communication. We don't need quantum, right? We need, because when classical to quantum internet you are going, the only advantage, the only advantage you are seeking for is the security and the unconditional.
No. So that is the point of my talk, right? So when people think of quantum communication, they think only of this thing here, top left, right? So, and this is the only point we are discussing so far, QKD. But what I'm saying is that there is a hierarchy of quantum networks you can build. The most basic quantum internet would be classical internet, that plus entanglement or plus short range entanglement, which can let me do trusted node QKD. This would be the most basic quantum internet. But as you are able to distribute entanglement over longer and longer distances, you can do these more exotic applications, right? And as an example of that, I showed you something like...
We can continue discussion later, but this is not the thing I am saying. For example, the picture, you show me the picture.
So which picture?
First page.
Yes.
Is the picture you drawn in the middle, that there are many sources, right?
Yeah.
So if there is a many sources, you cannot prove that probability distribution, joint probability distribution, you can calculate, that cannot be convex. It's not convex.
No, is your concern that when we actually build a quantum internet, if we build a quantum internet like this, right?
Yeah.
You are saying that there has to be real-time analysis of the S parameter, for example, to see whether there is eavesdropping
No,
or
this
not.
is not my concern. My concern is I'm theoretist. So my concern is simply theoretical perspective.
Yeah.
If you take this kind of source, you have to prove at some point that your joint probability distribution, because you will be performing measurement. Quantum mechanics is not about the state; it's about the state and measurement, right? So when you get the joint probability distribution, in such a case, this type of sources, if you take multi sources, you cannot prove this is convex. If it is not convex, you cannot prove it is secure. That's the theoretical point of view.
So let me ask you this question. So, or maybe one way to understand is this. So you're fairly familiar with entanglement swapping, right?
Yes, but swapping is
so
secure.
Right. So if you have, for example, here, right, on this side, some pure entangled state could be phi plus, and on this side, it could be phi minus, right, or some two entangled states. And I do entanglement swapping here. I will get one of the 4 Bell state outcomes, right?
Yeah.
And then my node here and my node at this end will be entangled, right? So in this case, you agree that you have established a perfect quantum channel between this node and this node with capacity 1, right?
No, the question is, okay, maybe we can discuss
No,
later.
no,
This question is not like that. I understand that.
No.
This is not the question.
No. So what you're saying is standard, right? So in any kind of non-locality, you have to prove that there is no model which can recreate the same statistics, but does not use entanglement, right? That's what you're saying. Of course, I'm saying that is well established and people have moved on from that, and people have understood that, you can have entanglement distribution on pure states or on mixed states. Mixed states is more relevant for application because all of these channels will not be perfect. There'll be some noise.
Well, if you have some mixed state, then it will be extremely difficult to prove the security. Okay. So, but one more point I want to end this discussion, because I just want to ask that if the swapping protocol is truly quantum, truly non-classical or not, how to prove that?
You're asking me or are you telling me?
Yeah, I'm asking you. That is, I mean, if you accept that something is traditional, that is swapping is there, swapping is truly non-classical or not, you have to prove it. Entanglement is there. Whether entanglement, all entanglement does not give non-classicality. So you have to prove the non-classicality. So the whole quantum internet business, you have to prove that there's a security involved. Security, this has to be unconditional security. That needs kind of checking. That's a Bell inequality violation or something you need. That is, you cannot mimic your statistics by a classical model.
So I think that if you if you are familiar with entanglement swapping, right? So you know that it's a quantum operation, right? So entanglement swapping is a map which basically takes as input, 2 states, rho 1 and rho 2. They could be pure states, they could be mixed states, and it gives me some 2-qubit state in general after tracing over the degrees of freedom that I have measured, right? So this operation or this channel is quantum or not, you can classify whether it breaks entanglement or it preserves entanglement, or it has some channel capacity. So, but I think we're having a little complicated discussion about something pretty simple. So here's the thing:
you can have or not, that's also debatable. But okay, I mean, maybe we can move forward. And
do you have more questions or?
No, I don't have more questions. Maybe we can contact us earlier and discuss this.
Sure. So let me just conclude by saying that if you have 2 entangled states and I join them, I get a larger range entangled states, right? Right? So now, if you believe that one Bell state can teleport quantum information perfectly over a short range, then a longer range entangled state, Bell state, can also teleport information perfectly. So what you do with it, whether you do QKD or whether you do teleportation, is up to you. But okay, that's the thing. Yeah.
Okay, thank you. Thank you very much. So
Yep.
I think we are running out of time, and let us thank Dr. Siddhartha Santra for his interesting talk. Okay, thank you
Alright.
very much.
Thank you.